A zeroed 4-byte integer represents 0, 1 represents 1, 10 is 2, 11 is 3, and so on, up to the maximum value an integer can represent when all bits are set to 1. But what about negative values like -1 or -1000? These are also integers, right? How do we store those? And how does the arithmetic even work? Welcome back to Drilling Sessions. In the previous video, we explored how bytes work, what sizes mean in memory, and how type modifiers help us adjust them. Today, we'll talk about how negative numbers are stored in binary, what signed and unsigned modifiers really mean, and what happens when things go wrong, like overflow. Let's start. We can think of an integer as data consisting of two parts, a value and a sign. Let's compare two values, 10 and -10. The value they both represent is identical, 10. The only difference is the sign. The sign can have only two states, it's either plus or minus. So, as you might have already guessed, we can use a single bit to represent it. Let's say 0 corresponds to plus, while 1 stands for minus. This approach is called sign magnitude. Because one bit is now used for the sign, it no longer contributes to storing the value. That means the overall range an integer can store is reduced. But which bit should be used to store the sign? For simplicity, we'll use big-endian representation in scope of this video. Imagine we're working with an 8-bit integer. It doesn't make much sense to use a bit from the middle, because the sign bit would always be in the way during operations on the value. So, the two most logical options are the least significant bit and the most significant bit. If we choose the least significant bit, we shift the value one bit to the left and always treat the least significant bit as a dedicated sign bit, 0 for positive, 1 for negative. The same idea could work with the sign bit in the most significant bit, only the shift would go to the other way. So, in theory, either could work, but eventually the sign bit ended up in the most significant bit. This happened for several reasons. The most significant bit contributes the most to a number's value in binary, so by using it for the sign, the integer's range adjusts naturally, without additional logic. Arithmetic in binary is performed starting from the least significant bit, so having the sign in the most significant bit makes operations like comparison and overflow detection cleaner. And finally, it became de facto standard due to historical design decisions in early hardware and architectures. So, in sign magnitude, the only difference between 10 and -10 in binary would be the most significant bit set to 1 for the negative value. Seems reasonable, but there is a catch. Let's try adding 10 and -10 in binary. That's the same as adding two values and moving the sign, so we ended up with -20. Not what we expected. The hardware doesn't magically know that the first bit is special. It just adds binary digits. This means sign magnitude requires custom logic for every operation: addition, subtraction, and comparison. It gets worse. We end up with two ways to represent 0. It's wasteful and confusing. Let's try to change the way we think about positive and negative integers. We could say that a negative integer is simply the opposite of its positive counterpart, at least relative to 0. But what if we try to represent them that way in binary? Let's say a negative value is just the inverted version of a positive one. In other words, we flip each bit of a positive number and treat the result as its negative version. This approach is called ones complement. Here's how 10 and -10 look in ones complement system. This solves the arithmetic problem between positive and negative values, because now if we add 10 and minus 10, we get 8 ones. That's 0 in 1's complement, or more precisely, negative 0. By the way, this explains the name 1's complement. To get the negative version of a number, you compute its bitwise complement to 1, meaning all bits are flipped. But there's still an issue. Let's try to understand what value is represented by 8 zeros. That's 0 clearly. But wait, we just said that 8 ones is also 0, specifically negative 0. So in 1's complement we are still stuck with two representations of 0, and that means additional steps are needed in the hardware and software to make comparisons and arithmetic with 0 work reliably. It feels like we're almost there, but something's still off. Let's think about that minus 0 in 1's complement, 8 ones. How can we automatically turn it into a regular 0? Well, notice something interesting. They differ by 1. If we add 1 to 8 ones, we get 8 zeros. Problem solved. And it turns out this trick doesn't just fix 0. It's exactly what was missing from arithmetic in 1's complement all along. Let's take a closer look at an example. In 1's complement, you always had to manually add 1 after bit flipping to get the correct result. So someone had a brilliant idea. What if we just bake that plus 1 into the rule itself? And that's how 2's complement was born. Instead of just flipping the bits, we flip every bit, then add 1. This simple rule solves multiple problems at once. It removes the concept of negative 0, it fixes the need for manual carry correction, it makes arithmetic work out of the box using the same binary circuits, and it greatly simplifies hardware design. Prior to C++20, the C++ standard allowed compilers to use any representation for signed integers. But in reality, all major compilers already used 2's complement. As of C++20, it's now officially the only representation allowed by the standard. An 8-bit integer can represent 256 unique values, from 0 to 255. But if we take the sign into account, the same 8-bit integer now ranges from -128 to 127. That's because the most significant bit now carries the sign in 2's complement representation. In C++, every integer type can be either signed or unsigned. By default, integers are signed. These keywords don't change the number of bits used to store the value. What they change is how those bits are interpreted. Let's take a binary value 8 ones. As an unsigned 8-bit value, it represents 255. As a signed 8-bit value, it represents -1, thanks to 2's complement. Same binary data, different meaning. Now, let's say we have an 8-bit unsigned integer holding the value 255. What happens if we add 1? It wraps around the 0, and that's completely well-defined behavior. Unsigned integers in C++ operate modulo 2 in the power of n. So with 8 bits, adding 1 to 255 just wraps back to 0. No surprises, no errors, just circular arithmetic. But now, what happens with signed integers? This crosses the upper limit of an 8-bit signed integer, 127, and tries to go to 128. But 128 can't be represented in 2's complement with only 8 bits. The highest bit is reserved for the sign. So what happens? Well, we don't know. This is where it gets tricky. In C++, signed integer overflow is undefined behavior. That means the result might wrap, like unsigned, or it might crash your program, or silently produce garbage, or behave differently, depending on compiler version, optimization level, or target architecture. In short, it's unpredictable. The same applies in the opposite direction. If you subtract from the lowest possible value, you'd be trying to go below the representable range. minus 129, which again triggers undefined behavior in C++. Unsigned underflow, on the other hand, is well defined and wraps 2. How do we detect signed overflow? Here's where the most significant bit becomes incredibly useful. Let's say you're adding two signed integers. If both numbers are positive but the result is negative, overflow occurred. If both numbers are negative but the result is positive, again overflow occurred. This simple rule works because the sign is stored in the most significant bit. This is one of the major advantages of 2's complement. Overflow can be detected just by examining signed bits, without special flags or carry corrections. The signed and unsigned keywords aren't limited to just int. They can be combined with other size modifiers. For example, unsigned short or signed long. These combinations define both the bit width and whether negatives are supported. Let's summarize. Today we've explored the memory representation of negative numbers, so how signed and unsigned affect the interpretation of bits, and examined the overflow. Thanks for watching and happy coding!